Hi everyone, my name's Jeremy Julian. I'm a graduate student at the University of Utah. I am studying economics there. I'm in my last semester. I have also received my undergraduate degree from the University of Utah in economics. Currently I work for the school, for the athletic department as a tutor in economics, statistics, and mathematics. And many of my athletes that are in classes such as econometrics or even introductory statistics classes use the program Stata for their analysis. And a lot of them have a hard time with this program. And I think it's primarily because it can be hard to find resources to do basic stuff in Stata. At least it has been for me. Usually when I Google search something for Stata, it pulls up something that's a lot more complicated when in fact I just need a basic command so that I can conduct what I want to do. So I've decided to make a basic video today, at least on regression, linear regression, and future videos will come out for other commands that will be useful in econometrics and statistics. So let's first go over how to import data into Stata. Okay, if you go to the Files tab and you go down to Import here, you have a couple of options for data files. This is Excel, one of the common ones. Another common one is the comma separated values, which is the CSV file. We have other ones here. I've never actually had to use any of these other ones because most of the data I use are of these two, or they're of the type that you can just insert directly into Stata. You go to data and then you go to data editor here and you can enter in your data directly into Stata from here. Go back to data. If you want to look at your data, you have this option here to browse. Pulls up a similar screen and this lets you view your data and it gives you helpful information over here. Another option to browse is you can just type in browse and it pulls it up for you. So there are two ways to do that. Okay. I'm going to use a data set, sample data set from Stata just to show you how to conduct a linear regression. I'm going to pick auto, DTA, and DTA is the Stata specific data file. Pulled up all the variables over here. It's got the name of the variables and then a description, a label here, which is helpful to scroll over to view if you can't remember specifically what the names mean. Alright. So the command for linear regression in Stata is reg. This is a basic regression. There are other ways and other methods of regression, but this is a basic one that most people are going to use, so we're just going to go with this one for now. Type in reg. Now you're going to choose your dependent variable first. If you recall in a linear model, in fact I'll type it down here in the command, linear models are built up like so, where you have your dependent variable, which is y. You have a constant, often b0. You have another coefficient attached to your first variable, and then additional variables and constants attached to those. And this goes on and on and on. And then it ends with an error term. Okay, that's your linear model. In Stata, we enter in data first with our dependent variable. I'm going to choose price. I prefer just to punch the arrows over here so it makes sure that I spell it right. Another option is you can just type in the variable names. I'm going to click on all these variables here that I think have an effect upon the price of cars. Now that I have them all in, I hit enter and it pulls up your data output right here. Let's go over every part of this because I'm surprised how hard it can be to find information about this display. So the first column right here are our variables. This is our y variable, our dependent variable. These are all our independent variables. And then cons down here, this is our constant term. Coefficients right here, they're the betas or the b's that you saw in the linear regression that I had right here. These are estimated using ordinary least squares. It's a method to estimate coefficients. If we have a negative coefficient, such as this first one right here, this indicates that as miles per gallon increases, the price of the car decreases by $114.74. If we have a positive variable, like this one right here, this says that as, let's take a look at what the label describes it as, repair record. So as the repair record increases, I'm assuming that's repairs that have been needed since 1978. I may be wrong on that. I'm not sure of the description of that. But as that increases, the price of the car increases by $710.87. This constant term right here, the interpretation of this is that if all these other variables were zero, this is the basic price of the car. Okay. These are our standard errors. They're similar to standard deviations. They tell you how accurate wouldn't be the proper term, but they tell you how precise the coefficients are, these coefficient measurements. Higher numbers obviously mean greater variation, and the less precise our coefficients might be. Okay. This is our t-statistic. Stata calculates our t-statistics for us so that we can use it in hypothesis testing. These t-statistics correspond to each individual variable. The null hypothesis for these variables is that their coefficients right here are equal to 0. So if we have significant evidence from our t-statistic here, we can reject the null and conclude that this number is possibly the correct population value for this variable. Over here we have the p-value for the t-statistic. It's the probability attached to these values over here. In hypothesis testing, we use a measure, a bar, if you will, that we compare these two. Often that is a significance level or an alpha of 0.05. That's the common one used in social sciences. We compare these probabilities, these p-values, against that 0.05. If this probability is lower than 0.05, it's statistically significant. So in this case, we look at this variable, it's lower than 0.05, and so rep 78 is the coefficient is statistically significant, meaning that it's not equal to 0. The true population parameter is probably not equal to 0. We have other ones here, so this one's also significant. This one's close, but it's not significant at a 0.05 level. And then we have other ones that are quite high. This one is extremely high. So we would have to conclude that the true population value based off of our sample data is 0 for this coefficient. Over here we have our confidence intervals. This is set up to do a 95% confidence interval. What this means is that if we could take an infinite amount of samples for this data, and then we constructed confidence intervals, that 95% of those confidence intervals would contain the true population value. Okay? It doesn't mean we have a 95% probability of getting the population parameter. That wouldn't be the most correct interpretation of 95% confidence interval. my previous explanation would be the most correct for these. So if we looked here for miles per gallon, this confidence interval says that the true population value for this coefficient here is going to fall within this range. Okay, so there could be a chance that if we sampled data randomly, that we could end up with a positive coefficient given the data. All right, this right here, this area right here, is for your ordinary least squares, which is used to calculate your coefficients. These are the sum of squares, and this is your mean square. You have your degrees of freedom right here. These degrees of freedom are used to calculate your F statistic. You don't really need this unless you have a paper that's really descriptive in methodology. For most papers, you wouldn't need to report this. It's important to understand how this correlates to this and to your F statistic over here. This is the number of observations. So in this data, we have 69 observations. This is our F statistic. It's calculated. This statistic differs from this statistic in that it tests the significance of all of these variables here. Okay, not just the individual coefficients, but all of them. All right, and again, this is the probability of F. It's similar to the p-value here. If it's lower than our significance level of 0.05, we can conclude that this model is significant, okay, that we have significant evidence for this model. The R-squared is the goodness of fit measure. It tells us how well our data fits to our linear equation, the equation that I had down here, I showed you. It tells you how well it fits to that fitted line, okay? And that's R-squared. Adjusted R-squared, in my opinion, is the more accurate measure, because as you include additional variables, the simple inclusion of a variable increases this R-squared. Okay? So what we do with the adjusted R-squared is we adjust the R-squared for number of variables included in the model and the sample size. So that way, as we increase and add additional variables, we won't see a dramatic change, or we shouldn't see a change in our adjusted R-squared. The root MSE, this is the standard deviation of the error term. Okay, so it's similar to this right here, but it's for the error term that I showed you in that linear regression. All right, and that's the basics on output for Stata, and that's the basics on how to run a linear regression and some of the basics on how to interpret your data. So if you have any questions, go ahead and email me, or you can go ahead and post something, and I will try to respond. If there's something more that you want to see about this particular topic, let me know as well, and thank you for watching.